So folks, in the last video, we looked at how to find the inverses, or the inverse of a 2 by 2 matrix. And we showed two different ways of doing so. The second one that I showed you was how to use a formula to compute the inverse of a 2 by 2 matrix. So we use this formula here, but that only applied to a 2 by 2 matrix. The more useful version, because it's more generalizable, is to use the row reduction method, where we're basically solving the system of equations for the entry of what we want the inverse matrix to be, to force the product to come out to be the appropriately sized identity matrix. And that's what we're going to do here. So I'm going to take A and augment it with I. So I chose this example for two reasons. One, because it's messy and it has fractions, and that's just the nature of working with matrices. It's almost impossible when you're looking at inverses to not have fractions if it's just coming up to you in the real world. The second thing is we have a situation here where this 1-1 entry is 0. And so, although we don't always have to do this, I want to make sure you see this step. If the 1-1 entry is 0 and you're trying to perform the row reduction algorithm, you look in the column that you're currently working in and seeing if there are any rows with non-zero entries there, and if there are, you're going to swap it up. So in general, though, the row reduction algorithm doesn't ask you to do swapping unless you have a situation like this. So it's important to me that you don't swap rows unless you need to for a situation like this. In most of the problems I give you, especially questions on tests, you will not encounter fractions when you compute inverses, but those are kind of cooked up problems. In the real world, you will encounter fractions, but for my class, I would like you to follow the algorithm and not just swap rows as you wish to try to avoid fractions. So, long story short, I don't have a non-zero entry in that position, so I'm going to swap these two rows. So I'm annotating that I'm swapping the two rows, and in this case I'm annotating that I'm leaving the third row alone. Usually I don't annotate that. My next goal is to get a 1 in this first pivot position, and the straightforward way to do that is to say that my new row 1 is 1/5 the old row 1, meaning I'm dividing that first row by 5. Now that I've got a 1 in that pivot position, I now want to get zeros above and below it. Well, there's only a below, so I need a 0 here. So the way I'm going to do that is say that I'm going to take -3 times the current row and add it to the current row 1 and add it to the current row 3. And already you can see that these fractions are starting to get a little unwieldy. For instance, when I multiply this entry by -3, I get -3/5, and I'm going to add that to the current entry of -3, which gives me -18/5. Likewise, I'll multiply this entry of -1/5 by -3 for a positive 3/5, and I'll add it to -3 for a -12/5. And I did the same thing with this entry. At this point, we've finished pivoting off of this column, so we move down 1 and then over 1 to our next potential pivot position. Because it's possible to get a non-zero entry here, it is going to be a pivot column or a pivot position, and I've already got a non-zero entry there, and in fact it's already 1, so we're in pretty good shape. Now I want to get zeros above and below it. To get a 0 above it, I'm going to multiply my pivot row by -1/5 and add up. And to get a 0 here, I'm going to multiply my pivot row by positive 18/5 and add down. Getting close to finishing. I've now got a 1 in this pivot position as I wanted, and zeros above and below it. I now need a 1 in this pivot position. So to do so, I'm going to take my current row 3 and multiply it by 5/6. So if I multiply this entry by 5/6, that'll give me the desired 1 there. Now we're almost done. We now just need zeros in these positions. To get a 1 in this position here, I'm going to take -1 times my, so I'm going to say my new row 2 is -1 times my current pivot row plus my old row 2. And to get a 0 in this position, I'm going to multiply my current pivot row by positive 2/5 and add up. And so this matrix right here, and I haven't really left myself enough room to recopy, hopefully, maybe you do, maybe not. And so if we wanted to write matrix A inverse, which I believe was the name of it, matrix A inverse would be 1, 0, 1/3, -2, 1/2, minus 5/6, and 3 minus 1/2, 5/6. Folks, the reality is because of all this division, most times when you do these procedures, in the real world, you'll have pretty messy fractions. In fact, they can get unbelievably messy as far as the fractions go. What I'd like you to do, though, is I'd like you to go ahead and find the inverse of this 3x3 matrix. Go ahead and stick to the script with a row reduction algorithm, and you will not have any fractions when you complete it. So give that a shot, folks, and let me know if you have any questions.